Okay, how did this problem go? How many of you completed this problem? Probably just one of you. All right. All but C. Good job. Let me turn the lights off. Yesterday, when I told you how to do this, I told you the wrong way. And then we fixed that. And then for C, I said, hey, that sounds like a half-life problem. And that actually led you astray, most likely also. So we'll just take a mulligan and say, my bad. It was a Monday. The good thing is next week there isn't a Monday, so we should be fine. Right? The even better thing is next week there's only one day of school for me and Post. All right. Just 'cause. And the good news is, as of when I went to bed last night, the government had made an agreement to stay open. So I think, thank you, Isaac. Wow, that's a cold pencil. Yeah. I think that we'll actually get to go to the Capitol and the White House. Yeah, instead of looking at them with their doors shuttered and the bars in the windows. All right, here we go. So determine the order. When this was doubled, the rate doubled, right? All right, so for H2, it was a what? It's a first order reaction. Who was successful in doing that? Okay, that's a good sign. All right, then when this one doubles, right here, that's a 2, right? What happens here? That's a 4, correct? All right, so NO would be to the second. So that would answer this. For the reaction of NO, that was a 2. H2, that was a 1. The second part, right, the overall rate law, that would be rate equals K times that squared. Okay? So what would be awesome here is without much work, you already would have 3 out of the 9 points on that AP test question. And I know that seems low, but once again, if you can average between a 3 and a 4 out of 9 on every question, that's a 3 on the test. So yes, you can fail miserably and still pass. All right, next, calculate the value of the rate constant K for the reaction, include the units. All right, so to solve for K, now I know this information. I'm just going to substitute the top row into this equation and solve for K. So remember, K equals rate divided by that stuff. Okay, let me write that over. So K will equal rate divided by the concentration of H2 and NO squared. So I just plug stuff in where it goes. All right, the rate is 1.8 times 10 to the negative 4. I'm going to plug all that in right here. So 0.00018. And I'm going to divide that by the concentration of H2, which is 0.001. And then NO is 0.006. But I will square that value, right? And that tells me K is 5,000. Anyone want to back that up for me? Okay, 5,000. Don't panic if K is huge or if K is small. It happens. Okay? So K is 5,000. Now it says that would be a point, and then it says include units. That would be the second point for this problem. So I'm going to take this same fraction here and put it here, and then just put the units. All right? The rate was mole per liter per minute. So I have mole on top, liter on the bottom, minute on the bottom. You okay with that? I just got it from there. That's the unit of this piece. All right? These are moles per liter. Okay, but they're in the denominator, so they're really written in this upside down. Is everyone okay with that? So really, it's liter per mole. and then it is liters squared per mole squared. Where'd the square come from? Tell your partner. Okay, the square came from here. Since NO was to the second, its unit was squared. But remember, since it's in the denominator, when we write it out this way, it flips everything. Okay? So now I can cancel some stuff out. I'm going to cancel out the liter right here, the liter right there, the mole right there, the mole right there, and nothing else cancels out, correct? So the overall unit for K here would be liters squared per minute mole squared. Is that a weird unit? Sure. But it's what it is. K is just a number that makes everything talk to each other, and it needs to be a unit that makes all the units cancel out correctly. All right. So there we would have, so 1, 2, 3, 4, 5 of the 9 points that would be on this test. That would be awesome. Okay, for part C, it sort of is a half-life, but we're not going to use half-life at all. And I'm going to introduce something that we have not ever used before, but we're going to use a ton in the next 3 or 4 chapters. So, what I'm going to do, I'm going to take this equation right here, and I'm going to write it again on this other part. Now, I'm really only going to worry about NO and H2, and I'll show you why I'm doing this in a minute. 2NO plus 2H2. I don't know why I put 2 H's. But whatever. Oh, are you serious? Whatever, that's a 2. Okay? Goes to, and I don't really care. You all right with that so far? Okay, this is a new concept, but it's one we will use a ton. I'm going to put some vertical lines right here. Okay, now, these tables are called ICE tables. We will really use them a lot in chapters 15 and 16, like a lot. They're called ICE tables because this row is I, this row is C, and you can probably guess what this row is. E. I stands for initial, C stands for change, and E, we're going to learn, stands for equilibrium, but for now just put E means the end. Okay, so what an ICE table will do is it helps you find either the change or the end of one thing, knowing the change or end of the other. I know that sounds a little odd, but let's go for it. So coming back to this problem, now by the way, there's 3 or 4 of you that could have reasoned this through in your head, and that's fine. Send it. If you can do it in your head, I have no problem with that. But the rest of you should do an ICE table. So here we go. It says for experiment 2, calculate the concentration of NO remaining when exactly 1/2 of the original amount of H2 had been consumed. So what I'm going to do, I'm going to come up and I'm going to get my initial values for my reaction. 0.006 and 0.002, and I'm going to put them right here. All right, so far is that all right? We put the initial concentrations, it told me, in the initial row. Okay? We could do this for every part of the reaction, like where I put the dots, but I don't need to in this question because it wants me to compare this to that. So that's the only data I need. Now, that question, one more time, says the following. In experiment 2, calculate the concentration of NO when exactly 1/2 of the original amount of H2 had been consumed. So I know that my change is half for H2, correct? So H2 is going to go to 0.001. Okay, sorry, that's technically, we're going to write that anyway. The end is 0.001. Because that's half of what I started with. Are we okay with that? Now, I know the other number is going to be the same because it's half. and I didn't need to erase, but I wanted to make sure I did that right. So my initial was there, my end is half of that value. So I come over here and my change is 0.001. The change is just the difference between my initial and my end. Can I get a thumbs up? Is that okay? Okay. Now, we're going to apply stoichiometry, which sounds hard, but it's not. Stoichiometry just means, hey, look up here. This is a 2. This is a 2. So whatever change happens here is exactly the same as the change that happens there. Does that make sense? If the coefficients are the same. So I come down here. My change is 0.001. Now technically, these are both negatives because we are reactants that go down. So now I take 0.006 and I subtract 0.001 and I get 0.005. That is the concentration of NO when exactly half of the H2 has gone away. Yes. All right, if it doesn't have a 2, then we have to do some stoichiometry. So let's pretend it's just a 1. All right? So now, if it's a 1, for every 2 that are consumed, 1 of these is consumed. Is everyone okay with that? So that would mean my change is half of what that was. It would be point. Oh, come on, Tom. It would be that, and then this would be 0.0055. Okay, so we just apply the stoichiometry: 1 to 2, 3 to 2, whatever we have to do. Okay. Most of the time, it's going to be pretty simple, meaning it's going to be the same, or one will be a 1, one will be a 2. It never really is any worse than a 2 and a 3, or a 3 and a 2. All right, so that is how you answer part C. It would be, remember this was really 0.001, so it would be 0.005. Ice tables will become invaluable to you. We'll use them a ton. We won't use them again in this chapter, really. But the one on the test is like this, so I can't remember if I even have a part C on that one or not, but whatever. All right. Describe the appearance of nitrogen gas to the disappearance of hydrogen gas. This one should be a nice softball here. So we already talked about it yesterday, but we'll do it again. Nitrogen appears with a 1, correct? Hydrogen disappears with a 2. So you can say it wants it, the appearance of nitrogen, it appears at 1/2 the rate that hydrogen disappears. If it was reversed, you'd say that hydrogen is consumed twice as fast as nitrogen is made. So you're just describing the coefficient ratios just in words. Okay. Are we okay with that? All right. Now, E. E's nice. A little bit ago we said the rate was equal to K. Is it NO squared or H2 squared? And H2 to the first. All right. So it says the following sequence of elementary steps is proposed mechanism for this reaction. And it has this. So what we're trying to do is to determine the rate determining step or the slow step. So based on what we learned yesterday, the rate law consists of all the reactants in the slow step and before the slow step that were not intermediates, correct? So what we're looking for, make sure this clicks. Since there's a 2 here, we're looking for an NO and an NO. Now you can see that in this first step, there's an NO and an NO, correct? So, but do we also have an H yet? No. So the top one is not the slow step. Then I'm going to cancel out these intermediates. Then here I have a single H2. Does that now include a single H2? Yes. So I would say the second one is the slow step. Because if the third one was slow, tell your lab partner what would be different about your rate law. Okay? H2 would also have been squared, correct? Okay? So, once again, you find how many of these there are, and once you've met that, that is your slow step. This one wouldn't matter at all. Okay. This one's a little bit hard. All right? And I don't know, that one to me is the hardest question of this whole thing. So this is one, hopefully you could at minimum get 8/9 on your test, which means on the next free response, if you can just get 2 out of 9, you're actually doing really well. Okay? So rate laws, AP tests, rate law questions are usually some people's favorite because they're an easier place to get points. This did say explain your reasoning, I guess. So this part would have been 1. This part would have been 1 point. Your reasoning would have been something about that by step 2, all parts of the rate law are represented. That's all you really need to write. And so that meant that the second step was your limiting reactant. Or not limiting reactant, sorry, your rate determining step. All right. Okay. I know it's complicated. It took us 16 minutes to talk through it. But it's a good, solid question.